Good morning, everyone that is joining us today. We are holding today our first scientific workshop of our project, Surefit project. And I will just quickly go through this agenda today. So we will start with a very quick presentation on this project. What are the aims and objectives, and also the consortium. And then this will follow by 3 presentations with the results we have been achieving so far from the project. So the first presentation will be by Solimpex, by Sami. We will have then time for some questions from the audience. Then we have another presentation from Nottingham University, again questions and answers, and then at last from Aalto University. So said that, I will then jump into, if possible, let me see if I get this, just a second, jump into a quick overview of our project, our Surefit project. So this is a 4 years project funded by the Horizon 2020. It started in September 2020 as well, and it will remain till 24. So I guess, as we are all aware, buildings represent a big portion of energy consumption and also, of course, CO2 emissions. So our main objective is to reduce energy consumptions in buildings, residential buildings, and we will do that through different specific objectives. Firstly, we want to ensure a fast-track renovation of domestic buildings, implement prefabricated technologies, targeting near-zero energy buildings, increase the share of renewables in these buildings, and very importantly, and we will be focused on some of them, to create innovative technologies for heating, cooling, hot water, lighting, and power generation. There will also be some smart controls to make this all work in a very efficient way. And the technologies that we will be proposing will be demonstrated in 5 buildings. 5 buildings that are distributed in 5 countries in Europe, so we can have different climates and understand how they behave. At the end of the project, we aim to develop guidelines and an operational tool in order to replicate fast-track renovations all over Europe. And at last, of course, we will also be looking at innovative business models in order to commercialize these innovative technologies. So the consortium includes different partners in Europe, from different countries, but also from a different nature. So we have research institutes, we have academia, but we also have a large share of companies that are producing these technologies and are willing to get them into the market. We have ISQ from Portugal that is also coordinating the project. We have AMES from Greece, University of Nottingham from UK, PCM Products from UK, Winco Technologies from France, CGR from Portugal, Solimpex from Turkey, Costa from Germany, Santa Maria del Real from Spain, On Control from Portugal, and Aalto University from Finland. So, as somehow mentioned through our specific objectives, there are a couple of technologies, innovative technologies that we are developing in the project, and in order to understand how they behave, we will be implementing them in 5 pilots around Europe. They are manufactured by industrial partners that are part of our project consortium, and we are going to test them in 5 climates: Mediterranean climate, Atlantic and North, so Portugal, UK, Greece, Spain, and in Finland. So this is a very quick view of the sort of technologies that we are exploring and testing. We do have, I'm going to go a little more in detail in the next slides. We do have a solution called PV vacuum glazing window. I'm not going too much in details because my colleagues, the partners, will be presenting it shortly. But yeah, we do have a PV vacuum glazing with a PV layer. We do have bioaerogel insulation blankets, breathable membrane, PCM in solution panels. As we can see, so far we have talked mostly on passive solutions, and we also have active technology, such as solar-assisted heat pump, heat pipe for the ground, heat ground. We have window heat recovery and evaporative cooler. also PV panels and a solar collector, as well as daylight louvers. So there are a combination of passive and active solutions that we want to implement in 5 pilot buildings. So as we can see in the map, we represent these pilots cover different climates in Europe. We have one social house in Portugal, in Mafra, where we have already somehow figured out which sort of technologies we would like to install in there, based, of course, on the climate. We do have a small apartment in Spain, in Greece, apologize, on the right hand. A semi-detached house in Nottingham in UK, a prefabricated house in Finland, and at last also mill houses in Spain. So this was a quick introduction to our project. You can always visit our website, surefitproject.eu, where you can find all the details. We have been actually very active in sharing. Thank you, IMES, for that. We have been sharing actively our results and progress of our project. So if you are more interested on it, you can quickly access to it. So said that, let's then start our scientific workshop today. Our first presentation is about CFD analysis of a hybrid PVT collector cooled by forced water circulation, and this will be presented by Dr. Mahmoud Sami from Solimpex.
So Sami, I think, has presenting privileges now, so he can share his screen.
Hi. Sorry, can you hear me now?
Oh, yes.
Oh, okay. Sorry, I just dropped from the internet. So is it my turn now? Sorry for the mess. Okay, I'll share my screen. Nope. Sorry, Thames, I cannot share my screen now. I don't know why. Can I just...
You are a presenter, correct?
Mm-hmm.
Okay. It seems I have given you the privileges now.
Mm-hmm. Let me try again.
Sami, if you want, meanwhile, we can change the order. There's not a problem. We can start with the second presentation if you want to.
I think he's disconnected.
Okay, so then let's move to the second one. We will start with second first.
Okay.
So energy performance enhancement of solar assisted heat pump and building integration PV thermal storage system and the different climate contexts. And that will be here with my colleague, Dr. KQ from Nottingham University.
So I think you are presenter now, correct?
Yeah.
Okay, that's nice.
So you can present, yeah.
Can you see the screen?
Yes, we can see it.
Okay, all right. So welcome, good morning. My presentation today is about to describe the an integrated innovative system, which is called the PV thermal storage system integrated with solar assisted heat pump. Here it's called PV SHPTS, and we are going to investigate it under different climate context. So to be beneficial, that the solar assisted heat pump is has a lowered freezing temperature refrigerant in the evaporator side, and the surface temperature of the solar assisted heat pump is crucial for the coefficient of performance of the system. And from the literatures, we find that there are major four limitations, including the complexity of the whole system, the cost, the system degradation with long period operation, and the frequency of maintenance requirements. So by analyzing the challenges of the solar assisted heat pump, that some literatures have proposed that fast responsible heat storage, heat exchanging units is important to be integrated into the residential buildings to avoid the mismatch between the heating demands of the building and the heat supply of the heat pump system. And also it's that the energy storage is essential for providing in providing the electricity and the thermal energy when the demand is high for small-scale standalone renewable energy system. So, and also the batteries and hot water storage tank could be considered as practical technology for PV electricity and the solar thermal short-term storage. So basically, I will describe the concept of the solar assisted heat pump. Similarly to the conventional heat pump that we can see from the following pictures, that we have condensers, compressors, expansion valve, and evaporator. But the evaporator here is replaced by the solar thermodynamic panels, and this is direct expansion solar assisted heat pump, and the heat from the condenser will be absorbed and stored in the hot water storage tank. When required, the hot water is being fed and to supply to load. And this is a prototype that we are going to use for the solar assisted heat pump that designed for residential buildings. We have solar PV panels on the rooftop, the solar thermodynamic panels, and the evaporator also on the rooftop. But both these two sides could be integrated as like PVT or some innovative technologies. The PV panels is generate electricity, which will support the operation of the compressor. And the refrigerant is flowing from the bottom side of the solar thermodynamic panels to the top side with absorbed heat from the environment and the solar radiation. And then it goes to the compressor with the normal heat pump work with heat generated from the condenser as the heat exchanger, and also the waters is flowing through the condenser with heat absorbed and stored in the hot water storage tank. So in this research, the PV solar assisted heat pump thermal storage integrated system is proposed as the electro-thermal energy storage system. The PV, as we described, the PV electricity will be support for the heat pump work. The heat stored in the hot water storage tank will be discharged when required. And then we did some modeling work according to different climate context as the building pilots located in the Surefit project for UK pilot, Greece pilot, Portugal pilot, and Spain pilot. And then according to the the figures we can see here, the X-ray is the surface temperature of the thermodynamic panel, and the Y-axis is the heating COP. And then we can conclude the formulations, the correlation of the formulations for COP with the temperature of the surface temperature of the panels with TP, and then we get the correlations from between COP and TP, and also the surface temperature of the solar thermodynamic panels is varied according to the equations here, which basically includes the solar radiations, GT, and the wind speed near the surface panels, which is V, and also the TA, which is the environment temperature near the solar dynamic panels, because the solar thermodynamic panels is observed heat from the environment and the solar radiation. So we can see the equations here. So according to the environment temperature, solar radiation, wind speed, we can get calculated the surface temperature of the solar thermodynamic panels, and then we can calculate the COP, heating COP in different pilots building locations. And then we move to the case study. So in this investigation, we have got the heating and cooling demands calculated via the IDA simulation software by the Auto University, and then we use this data. And here we use the domestic hot water demand and space heating demand, which is hourly data, and then we use our simulation software which is called Energy Pro, to integrate the solar PV panels, our heat pump, solar assisted heat pump, thermal storage tank, and the grid electricity to do the simulation. And here we can see the 4 building pilots for UK, Spain, Portugal, and Greece. And I have listed the avenue and the peak power and the demand for the space heating and domestic hot water. As simulation results, we see that there are 2 tables. The first one is that with only the solar assisted heat pump, and we have the data for calculation results. And then for our integrated PV SHPTS integrated system, we also calculate an upgraded system performance. As we can see, the most important for required solar assisted heat pump heating capacity, it's reduced from the first table. We can say 11 kilowatt, 20 kilowatt, 7 kilowatt, 26 kilowatt for different pilots. And then it's reduced to 6, 5, 2.8, and 7 kilowatt respectively. I have calculated that the reduced solar assisted heat pump heating capacity is reduced for 45%, 75%, 60%, and 73% compared between only the heat pump and also the integrated system. The main reason is for with thermal storage tank that we don't need that high peak load of the peak load capacity for solar assisted heat pump. It's reduced as we stored here, and we can also see the heating COP with only solar assisted heat pump and the integrated system. It's reduced. It's increased. We can see from only the solar assisted heat pump system, the COP is around 3.4 to 3.6, but with integrated system, the heating COP is increased to 6.2 to 9.0. And also, due to the increased COP, the integration of PV panels and the reduced heating capacity, finally the imported electricity from grid is also reduced from 27% to 61%, which have a large reduction. This is hourly performance data for the winter time, December, from 25 to 31 December. The first figure is about the heating demand for the heat generation for solar assisted heat pump and the heat consumption for only the solar assisted heat pump system. We can say it's matched between the heat generation and the heat consumption. Of course, we do not have any storage tank. And the second figure is about the electricity consumption, demand, and the required from the heat pump system. And this figure is about the performance of the integrated PV SHPTS system. And we can see from the first figure, the heat generation from the solar assisted heat pump is do not match with the hourly required heat consumption because we have the thermal storage tank here. So generally, the solar assisted heat pump is working at the daytime when there is electricity generation from the solar solar PV panels. We can see here, and then at the nighttime, the heat is generated and stored at the thermal storage tank. And over the nighttime, when there is or at the time there is no inflation, there is inflation solar radiation. The heat is exchanged from the thermal storage tank to support the heat consumption. And then we also did the economic analysis. As for, I will take the example of the UK pilot buildings. And the first table is about the cost that we calculated for the UK pilot buildings, which also includes the insulation for walls and the glazings, because we need to reduce the heating demand to fit with solar assisted pump. And also the cost here includes the PV panels, solar assisted heat pump, cylinder for hot water storage, and then we calculate the total cost. And then according to the data for October 2022, this year, this is economic parameters and the values for our calculations, including the interest rates, which is borrowed, and the inflation rate, the electricity price, natural gas price, the electricity increasing rate, natural gas increasing rate, and the calculated real interest rate. And we have the indicators for here for three items, includes the return on investment, annual return on investment, and the real return on investment. For return on investment, it's calculated by dividing the profits earned by on the investment over the period of years, which is the most general items. And then the annual return on investment is calculated according to the time weight annual percentage of the return on investment. And for the real return on investment, it's calculated by subtracting the inflation rate, which present in the more real return on investment. And we can see the table here. The left figure is about the annual return on investment with the variation of the inflation rate. And also we can see different lines here is the different the lower interest rate. And according to the data as I showed here, for 6.7% of interest rate and 8.6% for inflation rate, we are here, and it's around a little bit higher than the inflation rate of 8%, which we get the annual return on investment with a ROI of around 8 to 10%. And also from the right figures, we can see the deflation rate zone and inflation zone, with inflation rate the same and the interest rate the same. And the y-axis is the real return on investment. We can see here now we are higher than the 0%, which we have profit even at high inflation rates area. And this is a variation according to the annual return on investment according to different natural gas price increasing rate and the grid electricity increasing rate. And also we can see a circle here is where we are according to the data in October of 2020 of 2022. And we can see with the increasing of the natural gas price, there is a significant increase of the annual return on investment. The same are here with the increase of the inflation rates, we have an increase of the annual return on investment. And also with the increase of the grid electricity price, it's almost stable for the annual return on investment, especially except for the if there is a reduce of the natural gas over here at the bottom. So we can conclude from the investigation that an innovative PV solar assisted pump thermal storage integrated system, which is called electro-thermal energy storage system, is proposed in this research to provide both the space heating and hot water for residential buildings. And the COP correlation of the solar assisted heat pump has been derived according to different climate context, which also integrated here for building pilots. And by using the integrated system, we can see a significant reduction of the electricity, the grid electricity from 27% to 61% in our building pilots. And also this heating COP is increased from 72% to 156% to the maximum value of 9.2 with the integrated system compared with the only solar assisted heat pump system of 3.4 to 3.6. And finally, from the economic performance analysis, we see that this integrated system has a good economic performance, especially during the periods that we have a high inflation rate and also the high increased electricity and natural gas price. And that's all my presentation. Thank you for listening. Anyone have any questions?
Okay. So someone was asking, Sharon was asking, which is the kind of refrigerant that we use in this technology, refrigerant?
Okay. So in this refrigerant, in this system, we use R134A, which is normal to be used in heat pump. So it's no difference from other heat pump systems, which is convenient.
Another question is is the PV power consumed in the heat pump operation? So the PV panel is
the PV panels generates the electricity, and this electricity generation at the daytime is supporting the compressor work, so it will support the heat pump working. And we use the thermal storage tank to store the heat, which as another kind to transform the renewable electricity to the renewable heat to be stored in the storage tank.
Do you know, there's another question, do you know how much percentage of this PV power is actually consumed by circulating pump and heat pump compressor?
For the PV panels, we can see here. we can say that it imported electricity from the grid. For example, take the UK pilot as example, it's 5.9 megawatt hours for integrated system, but without integrated with only the solar assisted pump, it's about 8.1 megawatt hours. So we can calculate the reduced electricity here is 27%. So which means almost that 27% here for UK pilots is the electricity is replaced by the PV panels. And also it's varied according to different building pilots due to the varied solar radiation.
Good. So there's another question. What is the size of the thermodynamic panel in meter square?
In meters.
Yes, in meter square. What's the size of the thermodynamic panel?
The thermodynamic panels, that's for UK pilots, that's 6 kilowatts. We require that is for 3 to 4 panels. That is basically required to make it safety to satisfy enough space heating in case of the serious climate. So we installed 4 panels for UK pilots. But if only the solar assisted pump is used, then 11 kilowatt is required. That means around 5 to 7 panels is required for the heat pump.
Okay. And so last question, Joe is asking, do you consider a PV and a grid hybrid system as another scenario? So using PV and grid hybrid system, is there any chance to do so?
To integrate the PV with
Yes, grid hybrid system.
With the grid hybrid system. Yes, we are considering that to integrate the PV panels with any other high innovative renewable technologies, and also that we are considering to integrate the PV panels with the solar dynamic panels as the similar concept of PVT, PV thermal collection panels in the future investigation.
Okay then, thank you very much.
Exactly.
Okay, for this presentation. So going back to our agenda.
Sorry, Thames, can I try again?
Yeah, good, perfect,
I am the
perfect.
presenter. Okay, Thames already shared. Okay, maybe
What should
I
I
can
do?
try.
Should I share or should you try once more?
No, I cannot.
You cannot. So I
No.
share for you. Okay.
Okay, thank you very
One
much.
second.
So we'll now move on to the first, the first that became the second presentation. So CFD analysis of hybrid PVT collector cooled by forced water circulation. This will be presented by Dr. Mahmoud Sami from Solimpex.
Thank you.
Okay. So every time you need to change the slide, please say next slide and I will change it for you.
Thank you, Thames. Thank you for your help. Good morning, dear colleagues. This is Mahmoud from Solimpex Solar. And I'm going to introduce Solimpex a little bit as a technology provider of Surefit project, and also mention about a glimpse of simulation studies that we carried out in Solimpex R&D. Our group of qualified engineers has done CFD studies, and although it's part of a huge project, I will share some of the findings with you. So I'm here to present the work today. Next, please. Solimpex Solar is a renewable energy company, and next, please, again, sorry. Previous one. Solimpex Solar is a renewable energy company producing solar thermal panels, PVT panels, boilers, thermal energy storage, solar tanks, and the heat pumps, as you can see on the screen, and some auxiliary equipments like mounting kits, solar hoses, etc., in an area of 25,000 square meter with 130 staff. Next, please. So our manufacturing line is based in Konya, Turkey, and we have also another branch in Izmir for domestic market operations. Apart from that, two other branches, one in Sales and the market over Germany, mainly for the European operation. Next, please. And we have a lot of more than 20 certificates assuring our presence in more than 80 countries. So we have Solar Key Mark. All our panels are certified by Solar Key Mark. Next, please. So I would like to highlight that R&D is the integral part of Solimpex. At Solimpex, we have R&D projects funded by the national R&D funding body of TÜBİTAK and international projects. Next, please. And also international projects mainly funded by the European Union. So intentionally listed the project list here because each and every major product that Solimpex is producing today is the outcome of an R&D project. So from the previous list, you can see that there are 2 projects about heat pumps, 2 projects about PVTs, solar tanks, and boiler projects as well. So we just developed these units as part of these projects, and then we commercialize and successfully sell all the Europe or around the world, more than 80 countries, I must say. So R&D is really important for us. I should highlight. Next, please. Thank you. So solar energy has a great potential, and while used for thermal and electrical energy generation, could be a solution to global climate crisis that we are facing today. So it could be one of the solutions to the climate change, global warming, and greenhouse emissions. Please, next. So PVT, let me introduce PVT. PVT is a technology that you can produce both electrical and thermal power at the same time. So circulating fluid inside the tubes attached to the PV layer, the backsheet of PV layer, not only we can collect the excess heat accumulated inside the panel, but also this could remedy the efficiency drop due to the excessive heat. So every 10 degrees increase inside the panel will drop the efficiency 1%. So you can see on the right hand side, you can see the Solimpex Excel PVT panel and this unit is commercially available now. Next, please. So in this study, our group of engineers conducted a CFD study of the PVT panel. Flow and thermal analysis were performed by ANSYS Fluent, and the research questions here are whether water circulation could successfully cool the panel as expected, increase the efficiency, and provide thermal energy. So these are the basic research questions that we seek answer by doing this study. Next, please. In the numerical method, so this slide and the next slide, the following tables include technical specifications, thermal, optical, and radiation parameters for each layer of this PVT panel we use in our model. So you can see the specifications the thickness and the area and the emissivity, absorptivity, and the other details you can see. And the next slide as well. Next, please. And also you can see the absorption coefficient, refractive index of glass copper, and also radiation properties of PV cell, Kevlar, copper, water, aluminum, etc. Next, please. So in the numerical model, which looks quite boring, I guess, natural convection due to the heating, the air inside the collector was considered, and specific heat, thermal conductivity, and dynamic viscosity of the air inside are taken as constants. The Buzinesque approach for the density changes in the warm air is applied. Finally, what we try to do, we try to approximately solve the Navier-Stokes equations by finite volume method. Next, please. So for the sake of simplicity and they overcome the limitations imposed by the model, there are several assumptions made as listed here. So all layers in the upper part are virtually modeled with the shell conduction method, as it allows solar load model to include a solid component in the radiation computing. So the solid surface must come into contact with a fluid domain so we can apply shell conduction. And also solar load model only considers reflections on the transparent surfaces, and outdoor conditions are modeled as constant thermal convection coefficient. So you know, from heat transfer, H is constant, and the radiative heat loss at constant temperature as well. So the air and water flows are considered laminar as well. Next, please. So in this CFD model, there are more than 5 million mesh elements were used, and the skewness was below 0.8, and the orthogonal quality was 0.17, which is good, acceptable. And simple algorithm was used as the numerical procedure. We use second order discretization schemes for pressure, momentum, and the energy terms, and also solar load model was applied. So next, please. So looking at the boundary conditions, water is used as a refrigerant. The cooling performances were investigated at 0.01, 0.02, and 0.03 kilogram per second flow rates under 600, 800, and 1000 watts per square meter solar intensities. Atmospheric pressure at the pipe outlets was applied, and the radiative effects on the inlet and outlet boundary surfaces are neglected. Next, please. Yes, these are some of the findings. So starting with the 1000 watts per square meter intensity and the 0.01 kilogram per second flow rate, the outlet temperature was found to be 34 degrees. So the inlet temperature was 15, outlet temperature 34. I should mention the H coefficient is a convective heat transfer coefficient, 10 watts per square meter times Celsius, and the outside temperature is 22.2 degrees considered. So the inlet temperature was 15, the outlet temperature was 34, and the total heat transfer is around 800 watts. So the area average temperature was found to be 52.89 degrees for PV cell surface, 52.24 for Tedlar, and nearly 51 for absorber surfaces. The thermal efficiency was 48.3%, and the electrical efficiency was around 19%, and the total efficiency, total yield is 67.3%. So if we didn't cool this panel, the efficiency will be around 17%. So we increased by cooling this panel. We increased the panel efficiency around 10%, and 10% in total, and specifically 2 points we increased. So the validation of the heat transfer values calculated by CFD was performed by using the thermodynamic properties. On the right hand side you can see the thermodynamic calculations, and also according to mass average temperatures obtained from the CFD, we verified both equations and findings by using the enthalpy values obtained from the cool property. So it was that our model is acceptable. Next, please. So similarly for the analysis, and this we increased the mass flow rate. We just increased the mass flow rate in this analysis from 0.01 to 0.02. So we double the mass flow rate and they keep other variation constant. So inlet temperature again 15. So when we increase the flow rate, you can see that the outlet temperature dropped. So, and also area average, the PV cell temperature dropped as well. Tedlar surface temperature dropped and absorber temperature dropped. But since we double the mass flow rate, from the right hand side, the equation MC delta T, you can see that the total heat transfer was increased from 800 to 886. One thing we need to consider, well, it is the pumping work. So we have to consume electricity to double the mass flow rate, and this will eventually drop the efficiency overall system. But here we just take the panel analysis as it is, and we didn't consider the pumping work. So outlet temperature 25, so a little bit dropped from the previous slide. It was 34 to 25 degrees, and PV, Tedlar, and absorber surface temperatures were dropped as well. But thermal efficiency increased, and the electrical efficiency was increased as well, because we successfully cooled the surfaces additional to 3-5 degrees. So this reflects on the electrical efficiency as well. It was 19.04% in the 0.1 kilogram per second mass flow rate, but it is 19.28% in the 0.02 kilogram per second mass flow rate. The total efficiency increased as well, so which is 72.02%. Next slide, please. So we increased the mass flow rate even more to 0.03 kilogram per second flow rate, and the inlet temperature again 15 degree. Outlet temperature dropped because the water circulating inside the pipes did not have enough time to capture more heat. I mean, it doesn't spend more time like the slower flow rates inside the panel. But since you are pumping more 15-degree water inside the panel, you cool the surfaces even more. Like PV cell surface dropped to 49 degree. It was around 50 in the 0.2 mass flow rate, and it is below 50, 0.3 kilogram per second mass flow rate. And the Tedlar temperature even more, 48 degree, and the absorber temperature 47.25 degrees. Again, we calculated the heat transfer from the panel, but we didn't consider the pumping work again. And the total heat transfer is 912.58 watts. And electrical efficiency even improved. It is 19.37%, and the total yield, the thermal efficiency increased to 54%, and the total yield is 73.68%. Next, please. So, sorry, previous one. Yes, we in here for the 1000 watt per square meter intensity values, we compare all the results here. So the key finding is, for instance, the temperature difference due to the increase in mass flow also causes an increase in thermal efficiency. So when you increase the mass flow rate, thermal efficiency also increased. So this reflects on the increase in the heat transfer as well. But considering the pumping work and the other heat losses in the real world, is the whole system. If you consider the pumping work, probably you have to decide and operate decision making whether pumping more water inside would be beneficial in terms of heat transfer and the increase in the electrical efficiency. So the question here, is it worth it? So you have to compare. We are comparing, not here, but generally we are comparing. So, and also heat transfer between PV, Tedlar, and absorber, they are stacked on top of each other. They are laminated, and so the heat transfer mechanism between these layers are mainly by conduction. Therefore, these layers are very thin, and therefore, since these layers are very thin, detectable temperature differences do not really occur. So it's very thin layers on top of each other. They are stacked. So therefore, between these three layers, the temperature difference is not really that high. And also, for instance, the electrical efficiency of PV cells was 21% at 25 degree. So for instance, when the outside is 25 degree, the electrical efficiency was 21%, but it will be 19 if it was merely just PV layers, if it wasn't cooled. So since we cool, it increased from 19 to 20.5% electrical efficiency. Next, please. Again, we repeat the same analysis for 800 watt per square meter and 0.1 kilogram per second flow rate. Next slide, please. I'm not going to repeat the same things again and again. And also previous slide, 800 watt per square meter intensity and 0.2 kilogram per second flow rates. And next slide, please. And 800 watt per square meter intensity with 0.03 kilogram per second flow rates. So the expected results were the same as 1000 watts per square meter intensity. So we just compare the findings of 800 watts per square meter intensity in this slide. Again, the key findings is, for instance, if it wasn't cooled, it would be 17.61%, because the highest surface temperature was detected 68.9 Celsius in 800 watt per square meter intensity. So we increased by cooling the PV panels. It was increased to 19%. And also from the contours, you can see that we can successfully cool the panels, and the layers and the temperature gradient you can see on the PVT layers. So the blue lines show that we can successfully cool the panel on the water circulating areas. Next slide, please. Again, we repeat the same analysis for 600 watts per square meter intensity, starting from the 0.1 kilogram per second flow rate, and following 0.2 kilogram per second flow rate, and also, next slide please, 0.3 kilogram per second flow rate. And at the end, we calculate next, please. Thank you. And so here are the comparisons of the results obtained for 600 watts per square meter irradiance. So the outlet temperature was measured as 28 Celsius at 0.1 kilogram per second flow rate, 21 at 0.2, and 19 degrees at 0.1 kilogram per second. And also thermal efficiencies were 51% for 0.1 kilogram per second, 56, and 57% for 0.3 kilogram per second. The highest thermal and electrical efficiency values are obtained at 600 watts per square meter at 0.3 kilogram per second flow rates. So the detected efficiency increase, electrical efficiency increase in here was 1.82% increase in efficiency was recorded. Next, please. So this is the conclusion in a nutshell. We can make many comments here, like increasing the mesh flow rates. How does it affect on the heat transfer? So if we increase the heat transfer rate, since the MC delta T, Q is equal to Q equals to MC delta T, M is the direct value that we multiply. So therefore, theoretically, if you increase the mass flow rate, the amount of heat transfer you conduct is increased as well. Inlet temperatures are constant. We keep them constant, and we just compare the outlet temperature. But if you increase the mass flow rates, outlet temperatures will drop. And also, consequently, PV temperatures will drop as well. Tedlar PV surface temperature, and absorber temperature, absorber surface temperature will drop as well. Thermal efficiencies would increase, and the electrical efficiencies would increase as well. Next, please. Concluding my presentation, the outlet temperature of the refrigerant decreases with the decreasing solar radiation, which is expected. So thermal efficiency increases with the increasing solar radiation. If the solar cell layer is effectively cooled, this is the one of the research questions here. And also, the panel temperature decreases with the decreasing solar radiation that we can derive from the previous table as well. And also increasing the mass flow rate increase the heat transfer coefficient, enhancing convection from stagnant air to the pipes. Because under the same radiation condition, the refrigerant flowing at high flow rates caused more heat transfer to the pipes, as we have shown in our graphs, so which will eventually affect the cooling of the stagnant air as well. So this is basically we have a group of engineers at Solimpex R&D, and we are conducting simulation studies. And through these simulation studies, this is one of the works that we carried out under Surefit project. And also before the manufacturing, in the decision-making process, these simulations were really handy tools that we saw the temperature, to see the temperature gradients and the use of materials, the size of the materials that we decide through this analysis. So apart from that, apart from the CFD analysis, we are conducting transist analysis. We are using mathematical modeling, EES, SolidWorks, flow analysis, flow simulations, thermal simulations, PVC simulations as well. So it is, we just moved from prototype engineering to more simulation engineering in our department. So it saves us time and economy as well. Thank you very much for listening to me, although it is a boring analysis and topics. I quite find myself. It was really my pleasure to be with you here today.
Thank you, Sami, for the presentation. Very interesting presentation. We do have a question here from Sharon. So he's asking, so there's a thermal conductivity paste between the PV and module and the heat exchanger pipes. That's actually a question, sorry, if there's any conductivity paste between the PV module and the heat exchange pipes, and if yes, what's the name and conductivity?
Yeah, it is welding. We are just welding, and we are just laminating and with the bake sheet, and we are just making sure that the PV layers has really good contact with the pipes.
Okay, then
this is more manufacturing aspects. Yeah.
Okay, so then I have also a question. I have two questions actually. The first one, have you also performed, or are you planning to perform any study on the thickness of the layers for this?
Thickness of the layers, Muriel, yes, we can conduct many studies, but at the same time we have to be in line with the manufacturing side as well. So yes, we can decrease the thickness, but if you cannot manufacture, so
and if it's expensive,
why wasting your time? So it is therefore.
So you made already somehow an optimal study on which is the thickness that you could produce, and it gives you good results, I guess, of the.
Yes, definitely, especially for instance the size of pipings and the mass flow rates and the size of the panels. We have many variations, variables actually to consider, and we are just considering each of them one by one. So we have a lot of simulation data already at hand.
And the second question is related with the inlet temperature. So I'm not sure if you assumed 15 degrees because that's maybe, I don't know, in Turkey, that's the supply water temperature from the grid?
No, no, this is it's not from the real case actually. This is basically we keep the inlet temperature constant because we wanted to see the how much temperature difference our panel can successfully deliver us. So like if it says because we keep many things constant. For instance, when the outside is 1000, the solar irradiation is 1000 watts per square meter. The outside temperature is not really 22. It is more than 35 in Turkey because solar is shining. It's like August in Turkey. So we just wanted the inlet conditions we just keep constant, and at the same time we wanted to see the worst case scenario. So solar is really shining very well, but at the same time outside temperature is a little bit cold, so we have a lot of heat loss to outside. We wanted to see that as well, and also we keep the water temperature inlet below the standards. So and we wanted to see the temperature difference that how much heating that we can that our panel can generate at hand. So it can. We have seen 2-3 things. One thing is we can successfully cool the panel and deliver relatively hot water as well, and also we can increase electrical efficiency.
It's good. You actually mentioned a good point. It's really, at least for other countries in Europe, I mean, like Portugal, of course, I know the grid temperature is between 10 and 12 degrees. So I guess you made really the worst scenario in this case because the efficiency will be much higher.
Definitely.
With 10, 12 degrees.
But the panels are not really connected to the water grid. Because we have buffer tank between because we are collecting all the waters and the circulating water through the buffer tank.
Okay, I get
so if you install PVT in Portugal, you can see our system very well.
Good.
We can send you some panels.
Oh yeah, we'll look forward for that. Do you have any questions? No. Okay then.
I have one question. Can I?
Of course.
Is K in Portugal or Idaho in the UK?
UK. Yes.
Okay.
This is a modern view here from the offices in Nottingham.
Okay, it must be very cold now.
Yeah. How many degrees? Okay.
Minus?
Outside. Minus
9 degrees.
-9.
Oh,
yes. 9 degrees.
I'll help you. Okay, thank you.
In Greece, we have 20 degrees, just to mention that.
20?
Yeah, we have 13 in outside now.
Look at the difference. That's very cold. It's really close. Okay. So, Sami, thank you very much for this.
Thank you very much. It was my pleasure.
I just mentioned in our message box that we will be, of course, AMES and TEMIS will be supporting us in putting this into our website. So all these presentations will be in there after today. So let's move on to the last presentation. That's the title is Energy Saving and CO2 Reduction Potential of a Finished Building Stock with Cost Optimal Deep Renovation. This will be presented by Dr. Risto from Aalto University. Hello, Risto.
Hello, and I try to share. Okay. Put it this in the presentation mode. Okay, I think you see my screen.
Yes, we do.
Okay, good morning from Finland also. We have also -9 degrees here, but we have 50 centimeters snow here in Helsinki. So welcome to skiing to Finland. So today I will talk about Finnish building stock and how we can save energy and what are the effect of different measures and Okay, I can share the screen. Okay. Okay, this way. So in this short presentation, I will very quickly couple of words about targets what we have in the buildings. I mean, in European level, and then I introduce some measures and how effective they are in the Finnish condition. And I first focusing mainly for apartment building in my presentation. And then finally, I will have a couple of words about the whole building stock in Finland and what kind of CO2 reduction we can potentially have there if we introduce all different energy saving measures what we have at the moment. I will give overview of the effect of here and also what we have in Surefit. We focusing there for the Finnish apartment building renovation, and that's I will a little bit talk about a little bit big picture there. But first of all, we have in European level targets to make reduction of CO2 emissions and 40% by 2030 and 80% by 2050. And lately in European Parliament, these numbers will be updated, so we maybe have new future in our legislation also a little bit more tighter values. But we have also other targets like increase or reduce greenhouse gases, and we introduced just before this Ukraine war, this 50-55 scheme, and that's meaning that 55 reduction of greenhouse gases from the starting target level by 2030. And the idea is accelerate renovation in the buildings, because if we think about effect of new buildings is quite marginal, because we only renew building stock maybe 1 or 2% at the moment, and idea of this 50-55 is accelerate that for the 4% or level like that we have more significant effect. So we have to do something in the existing building stock, and new buildings is not enough for the targets. And lately, when we have this war situation in the Europe, when Russian attacked for Ukraine, EU launched new scheme Repower EU, where the plan is rapid to reduce dependence of Russian fossil fuels and move to green transition. So at the moment we have in the tandem two things. We have to stop global warming and CO2 emissions, and also we have to move for the green production and get rid of the fossil fuels. Two things we have to do it at the same time, and that had ongoing in the many European countries in the different ways. So that is the big frame, and coming back, if you're looking for effect of buildings, residential sector is the largest. And like in Finland, it's about 2/3 of the total emissions for the buildings is coming from apartment buildings or residential building in whole. And that's important to look for that how we can reduce and how possible solutions are different age groups there. And that's very important when we want to make some kind of renovation plans, policy for that. We have to understand how we should do it with different buildings. And we should look for the cost optimal solution that we maximize to use money and get as high emission savings as possible, and at the same time have a lowest possible life cycle cost there in the buildings. And finally is the question that how much this is potential make a reduction in the whole building stock. And I'm focusing here for the Finnish buildings and building stock in my presentation, and because that is also the target for in the Finnish demo in the Finland there. So first thing I focus here that how much possible to reduce emission in old apartment buildings. And the thing we have first looking for the Finnish building stock or apartment building in Finland, and they are able to make 4 groups based off the construction year. And we have 10 different regulations for building envelope, air tightness and windows, and also we have different regulations for the building mechanical systems there. So roughly they can classify it or grouped for the 4 groups as it here before 1973, 73 to 2002, 2003 to 2009, and then after 2010. As we can see here that we have different solutions for ventilation. And like in Finnish apartment buildings, we have at least typically mechanical exhaust. Only very old apartment buildings have natural ventilation. But if we think about big picture, we have at least mechanical exhaust or even nowadays mechanical supply exhaust with heat recovery. And when we look for the building stock, we can see here is a specific energy consumption or heating energy consumption for those buildings. Old one consuming more, and then we have newer buildings. The target values and the consumption values are much lower. And also we can see here that the biggest part is coming for old buildings for the space heating. And when we go in very new buildings, this domestic hot water is quite significant. It's even 50% or higher in the new buildings. And in the new buildings, we can separate ventilation here because we have aerated unit. In the old buildings, space heating is covered, losses for envelope and also ventilation heating demand. When we're looking for the buildings, then also the other thing is that what kind of system we will implement it there. And typically in the cities, in urban area, we have district heating. And when we make a retrofitting, one option could be that we will keep district heating as it before, or we move to the ground source heat pump together with the backup electric boiler, or we have a hybrid that we have exhaust air heat pump and then we have district heating together in the buildings. So these are typical options that we have it at the moment for the apartment buildings. Like in the big scale bio fuel, it's not practical in the cities and there's a pollutants and other things, so that the practical, those are the 3 possible technical solutions that we can consider when we are planning for renovation. And here, this figure have a lot of information, and I think that first of all, this indicates one building group, buildings that are constructed before 1973. So oldest group what we have it here in our classes. And here is this indicate different Pareto optimal solutions. So all of them, they are optimized if we're looking for 2 parameters, which are emissions and life cycle cost. That is calculated to 25 years. And so all of them, the optimal solution to do it. And we can see possible to think which are the logical effect. We can see that what's the effect of solar PV panels, better windows, solar thermal wall insulation, doors, or mechanical ventilation are coming here. And anyhow, we can see here that if you're looking for the lowest emissions, and of course it naturally have highest cost is here, so it's optimal. If you want to have lowest cost, lowest emissions, the solution is here for technical point of view, but life cycle cost is highest. If you want to optimize life cycle cost, the solution is here, but we have higher emissions. Then for the emissions in the Finnish conditions at the moment, we have district heating is based off the fossil fuels, normally coal, a little bit natural gas. So it's 173 kilogram CO2 per megawatt. And electric production is much more cleaner, 81 till 133, and that is varied base of the months. And these values have taken into account in this analysis. Also in the life cycle cost, because this calculation have handled before the war, our interest rate was a little bit lower, and also energy prices are lower, what we can, if we put it existing values at the moment. So if I reflect that the situation at the moment, most of the investments are more profitable at the moment. Okay, but this is the big picture, and if you're looking for the Paretos more closely for two different groups, and in this graph, the colors, blue is indicated this old buildings. Then we have this second group is the little bit younger buildings. So we have only two groups here, and this is the starting point. If we make a renovation and we maintain the district heating, this is the Pareto optimal line. So technically we can have reduction from the starting point for 34 till 10, but if it's just looking for optimal case, life cycle cost point of view is here. So these costs are more profitable than original situation, because we can see that the life cycle cost of these points are lower level than original point. But if we see that if we're moving that for the air source heat pump, this automatically jump for the other line. We have much lower optimal life cycle cost, lower level, and also emission level. And in the second group, if we are moving from the ground source heat pump, we can see that we can have significant reduction from the cost. Okay, but this is the principle. But here in the table, these numbers are covered for the old buildings. So we have the cases here that this is the AB1 is the oldest building group, and we still want to keep district heating there, not change the major heating system. We can see here that this point C is the cost neutral point. So it's meaning that the cost level in the life cycle is the same that original system. We can see here that we can have 28% saving here, but technically if we investment more, we can have reduction even to 72. But if we change this building for the ground source heat pump, we can see here that the cost neutral point for the starting point is 80% of saving. So once more time, this point is the point that is not increase the cost, so the life cycle is the same that earlier. This point D is the most optimal cost level, so we can see that we can have 70% of saving, and then we are even save the money in the life cycle. And here with the ground source heat pump, we can have even 72% of saving of CO2 emissions, and we have a lower life cycle. So this indicates that this investment is very, very, how to say, effective and cost optimal for the building owner. Okay, there's a lot of other information I don't have time to go through, but this is also indicate what kind of technical solutions are implemented in different choices here. And so this D is the cost optimal, cost neutral, and this is the technical possible if we want to make only reduction of emissions. And the point B is something between here, C and A point, just indicated what kind of level is there. Okay, but this is the individual building, but what in the building stock, and we also have modeled the whole Finnish building stock. So we have apartment buildings, single family house, education buildings, commercial buildings, and different age groups, which are at the moment, starting year is 2020. And then we have target year 2050, and we have make a renovation there. So we have indicated how much original buildings are renovated of different age groups and building types here in this model. And this model is also taking account for the urbanization. So some cities in Finland are, the population is coming low, and some cities are coming higher, and also this included when we have to make energy consumption, also estimated effect of climate change, because outdoor air is warming up in the winter time. We can have savings there, even we are doing nothing there, because we have a global warming. So I jump up the results. So this is the original case, and this is the business as usual. So we don't have many changes for 2050. We even get there some savings because of building stock is updated. We have renovation anyhow happened because we have new building, and some buildings are covered for the new buildings. And then here we have thing that we keep district heating there and looking for this cost neutral. So it's meaning that we don't increase life cycle cost. This indicated that we can have here 61% saving. If we make this deep renovation, so it's meaning that we implemented the technology within the market, even they are not cost optimal, we can have 70% savings, and then in the heat pumps, the numbers are even higher, 67 or 73%. Then one thing here is we have here biomass food that is using in the Finland, mainly in the single family houses. It's just indicated as a separate part here because it's a little bit under discussion how we should handle the emissions of the wood. Is that the zero emissions or is it something else? So we just indicated what are the level there. So I jump after conclusion so that in the deep renovations reduce significant energy demand, and it depends about what is the starting year and what is the initial conditions and what kind of system we want to change there. But we can see here that we can reduce emissions 70 to 80% in the cost neutral way. So this meaning that life cycle costs are not increased. So they are paying back. So in practice, the payback time is 25 years, but technically we can have 70 to 80% saving there. And the lowest emissions savings are coming when we implement heat pump system because emissions for the district heating is higher than electricity in Finland. So heat pumps are quite optimal. And one thing, of course, I have to say that these calculations limitations is that they are looking for existing emissions, what we have in energy system, which is now rapidly changing because we have now much more renewable energies coming in the grid and in the systems there. So this is a little bit, this situation is what we have at the moment, but in the future it will change. Also, this economical analysis have done with situation before the war. So inflation, interest rates and energy prices are before the war. And nowadays, if we take the existing numbers, the results are different. And if I reflect that, I think that all the investments at the moment are much more cost effective. So this is my last slide. Thank you.
Thank you, Risto, for your presentation. I was just checking if you have any questions on our Q&A box. Maybe I could start with a quick question, just curiosity. So for the heat recovery system, is this study considering just multi-story buildings, or is it also feasible to do it in detached houses, like a singular residential building?
Okay, technically it's in all buildings, but it's meaning that we have to fulfill the demands of the building code, but there is the latest version of a building code make exception that if you want to implement natural ventilation there, you don't need to follow this heat recovery demand of ventilation. but you have to present calculations that your indoor climate is acceptable and your building is not overheating in the summer. And that meaning in practice that still we only have very limited buildings which are now used natural ventilation. So we have mechanical ventilation. So in practice that if you want to make energy efficient system where we have good indoor quality, mechanical balanced ventilation is in practice also in the single family house. And I give example, my house is original built 1980, about 42 years old. I have there heat recovery with balanced ventilation there.
Okay, so it's doable. So that, yeah, it's just not.
So it's a practice, but coming back, our building code was that it's not accepted to use natural ventilation, but at the moment there is option that you can have it, but in practice it's not much used because indoor climate demands and also this overheating. We have some challenges, and you have to prove that with your calculation and show that for the officer.
Correct.
Okay. I also have a question about your life cycle carbon emission calculations. Have you considered the grid electricity carbon emission change during the life cycle period?
So I didn't quote it. What can you repeat it? This part, like in what kind of?
Yeah, I mean, during your calculation of life cycle carbon emissions, have you considered the grid electricity carbon emissions change? Because it's normally like your heat pump scenario that the electricity from, I don't know, from grid or from off grid, it's the carbon emissions of electricity from grid is reduced probably in the future. Have you considered that in the life cycle analysis?
Okay, these emissions, what we calculated, I have in the slides the numbers what we are using in the district heating and electricity. They are official numbers what we have in our energy industry at the moment. And district heating is not changed monthly at the moment, at least not much, but electricity there's a variation. So in this analysis we are using the latest information what we have at that time when we carried out the simulation in the system. But now these emission numbers are changing rapidly. And there is some companies in Finland, like if I put name of the company like a Fortum, that's quite big energy company, they publish in their webpage the emissions. So you can see that the emission numbers. But it depends that which part of the city or which city you are in Finland, what are the emissions of your local energy company? They can be different. I'm meaning like a district heating, definitely. But electricity, they are coming from the common grid. And we have Nord Pool in Nordic countries, so we are buying electricity for Sweden and in practice maybe Norway. But the limitation at the moment that the fires and cable grid size is not high enough because there's a lot of demand in the Central Europe at the moment in electricity. So we are in the same thing. And before the war, we bought a lot of electricity for Russia, but that stopped already 6 months ago. We don't import any energy from Russia at the moment. Nothing. Absolutely nothing.
Good.
Good.
Good.
Yeah.
Yeah. So, Risto, there's another question here in our Q&A box. What are your suggestions for the buildings in developing and underdeveloped countries?
Okay, this analyze what we did it is the Finnish conditions, and I don't know that you are not able to reflect that exactly your cases, and I think you have to carry out your local calculation in your local climate. So I think you have to think about climate, you have to think about building type, and you have to consider what is the original situation you're building, when that is built, what kind of envelope you have it, what kind of system you have it, and like that. But like a Surefit, we have calculated the apartment building for different locations in Europe, like Greece, Spanish, Portugal, UK, and also we had the Finnish case calculated. But I think you have to consider your local conditions there and local situation, what you have it. And more likely, of course, the whole life is coming more based of electrical thing that I'm quite sure that in many places heat pumps are one good options and maybe PV panels. But it's not the standard solution. You have to looking for what is your local thing. So this is a little bit strange, how to say, wide questions. And we also have calculated even other project for Chinese rural houses in the North China, and you can imagine the solution there is a little bit different than what are in the like in Finland.
Okay. So thank you, Risto, for your presentation. Thank you very much. So we don't have any more questions here, and also I think we are getting on time to finish our. I want to thank you all of you for being here. Thank AMES for also supporting and Nottingham the organization of this workshop, all the presenters. And we would invite you to follow our project if you like this. We have more results in there. We have also been publishing some of our latest results. So feel free to have a look. I'll just write it again, the website in our chat, so you can get to it easily. And yeah, that's it actually. Thank you all. And we hope to see you soon again. Thank you.
Thank you.
Thank you.